All right, folks, so this is the fifth and final segment of the combined section 7.4 and 7.5. This was recorded several weeks after the first four. After reflection, it seemed like it was worthy enough to go back and talk about orthogonality in its own segment. That was something I had debated before, but I think it's worth a review. So here we go. Let me kick over here to the document camera, and I want to just kind of discuss a little bit, a little bit of background as to why this is an important topic, but I'm not going to go into it too much. So this is section. Technically, this is all in section 7.5, but to remain consistent with my numbering scheme, or the previous pages I've done, I'm going to call this 7.4. Really, this is page 10 that we're now working on. So let's talk about orthogonality. What does it mean for two vectors to be orthogonal? Well, orthogonality means orthogonality. So if two vectors are at right angles to each other, they are said to be orthogonal. So that's kind of the definition of what orthogonal means. Orthogonal. Sometimes I have a little bit of problem spelling that. Anyways, so why is this really important? The book doesn't do much motivation. It doesn't really explain why this is an important feature. But I want you to think about coordinate systems in general. There's some real advantages to using what are called orthogonal coordinate systems. And of course, the most obvious version of this is the so-called Cartesian coordinate system, where your x and your y coordinates are at right angles to each other. It creates, if you don't have this sort of system set up, then you can have ambiguities that occur in terms of coordinates. So if you said I'm at coordinate q equal this and p equal this other thing, then when it applies to certain physical properties as well as mathematical properties, the fact that those aren't orthogonal can sometimes create problems. So what you're not wanting to have is some kind of coordinate system that looks like this, okay, where you've got sort of maybe some other kind of coordinate p and q. It's not that you can't work with this. It's just that this makes the sort of calculations or this interpretation of physical motion and whatnot very complicated in a system like this. But now you might ask yourself, well, why don't we just always use a Cartesian coordinate system? Well, there are certain phenomena that are not particularly conducive to be using that kind of a sort of a coordinate system. So there are three basic ones that you'll see in most mathematical applications. This is one of them. You have the x, y, and then of course, if we put a third dimension in that, z, positive z, is kind of, if you can imagine this coming out of the page, is sort of this way. And in electromagnetism, sort of a second semester physics class, you may encounter this sort of behavior that if you were to take your hand and curl it into, along the x-axis and curl it into the y-axis, the z-axis is actually moving out of the page. And this is what's called the so-called right-hand rule. That is actually just it's a choice. It's a mathematical choice about how systems are supposed to work, but it is an agreed upon choice that all coordinate axes that are of value to humanity have this right-hand rule. The first coordinate, which is generally in Cartesian coordinate, is x. And when you do these in higher ordered systems, you actually would call this sort of coordinate x1, and y would be coordinate x2, and z would be coordinate x3, and then there might be an x4 and a 5 and a 6, so that you can work inside of systems that actually have higher dimensionality than just 3. Well, so this isn't the only kind of system that's used. Often you have something else which is called a cylindrical polar system. So if you think about a polar coordinate axis, which is just a two-dimensional, so we think about just sort of laying this on top of it, we have these circles of increasing radius. And then we have angles from the sort of nominal x-axis. So this is, so to just kind of put this into perspective, this is really what we've been doing with vectors, is we have sort of this xy coordinate system. You know, if you had a vector that's out here, you know, forget about the z-axis for a second, but a vector that's out here, we have this component version, which is like a coordinate, so to speak. And then we have this magnitude direction version. And this coordinate system doesn't use the labels x and y. It actually uses the label r and theta, which should look kind of familiar from what we've been doing with vectors. Now, to make this a three-dimensional coordinate system, you have sort of a polar coordinate system that would be like your x and y axis, and then you have sort of a z-axis that goes out of it, so that if you had any particular vector in 3 dimensions, it has a projection down to the xy plane, and I guess maybe our normal x-axis might be here, and the y-axis might be here. That's kind of a reference. But this vector has a projection in the plane of the xy plane, which has an r value and a theta value. And then this point has a certain value z. So if you're looking in 3 dimensions, this, I mean, we could assign points in an xyz coordinate system. We might have them in an r theta z. That's another possibility. The so-called cylindrical polar coordinate system is used extensively, especially in magnetism related to like wires and different sort of things like that. The third coordinate system that is predominantly used in three-dimensional mathematics is what's called the spherical polar coordinate system. And the hallmark difference, it's going to be very, very hard to draw this, but if you imagine that you have sort of, here's your normal x, y, and z coordinate system, then if you have a point that's out here in space somewhere, it has an angle that's associated. Well, this is maybe a bad way to draw it. Let me try it with z up top. So if we have z, x, y, so here would be your x, and there's your y. So we have, again, this x rotated into y creates this right-hand rule. So z is up. So if you have a point, let's say we have a point that's its projection lies in quadrant 1, the xy plane, but it has a positive z-axis, or has a positive z point. So here's maybe that vector looking in 3 dimensions, and its projection down onto the xy plane might look like this. So for this sort of a system, we're not concerned about the sort of spherical polar. We eliminate all x, y, and z and replace them with something completely different. So we have what's this symbol that's used is a lowercase rho, looks like a p, and this is the distance from the origin to the tip of the vector. So we have a sort of a distance portion, kind of similar to what we had with r theta, and then we have 2 angles. So we have first what's called the azimuthal angle, which is usually used as theta. It's identical to the angle that's used in the cylindrical polar system. It's computed exactly the same way, but then we also have this sort of an angle that is between the z-axis and the vector in question, and this is usually given the symbol phi, and it is called the zenith angle. Okay, so this is sort of what a spherical polar coordinate system looks like. You have rho, theta, phi that uniquely defines a point. So what is all this about? Well, what's key to this is that we can really use any one of these coordinate systems in space it really doesn't, it depends on the exact applications we're trying to achieve here. Sometimes spherical polar is better, especially when you're talking about like orbits and electromagnetism, especially when you're talking about point charges, spheres, that kind of thing. Whereas maybe a cylindrical coordinate system is more applicable to magnetism around wires. Cartesian coordinates obviously have a lot of applications, but regardless, the hallmark between all of these systems is that you create these unit vectors that are in the direction of these various coordinates, right? So it's kind of a little hard to think of, but the theta direction here is actually at a right angle to that projection. And the zenith, the sort of unit vector in the zenith angle, is actually at a right angle to the tip of the vector moving down to the xy plane. And then finally, the rho vector, the unit vector in the rho direction, is actually an extension of that vector. So you have this sort of, if you were to look at it, you know, kind of in isolation here, you have this sort of rho hat, phi hat, and then kind of, it's a little bit hard to put it in there because the way I've got it drawn, but maybe you have, there's your theta hat. And those create a little, sort of on the local scale, those create a miniature Cartesian coordinate system, which allows all of the applications of what you have in Cartesian coordinates to carry forward. So you're like, okay, well this seems like way beyond anything we're talking about in this class, and really it is. But it's sort of the thing that you'll see later on. What is the critical thing to take away from this is that you would like to be able to determine whether or not two vectors are orthogonal, if they are at right angles to each other, and you'd like to do so in a relatively easy way, right? So typically when you're working in a system like this, you will define a vector based on its components, its x, y, possibly z components, and then the question becomes, is that vector orthogonal to another? Okay. So what I alluded to in the past was that there's this equation that allows you to figure out the angle between two vectors. So here's the equation. Cosine of the angle between two vectors is equal to the dot product of those two vectors divided by their magnitudes. Okay, so this is sort of, if you want to find what the angle is between two vectors, you calculate this stuff out, and then you do whatever. Remember, when we developed these, we only talked about two-dimensionality, but this actually extends to three-dimensional vectors with it's pretty easy to get to that point. You just add another component, and then you compute the dot product exactly the same way. It's the product of components added together, and the total becomes the numerator, and then you're still dividing by their magnitude. Now, their magnitude is going to be determined a little differently because there's a third component. But regardless, here's the critical part. If these, and this is sort of a converse, the converse is true as well, but this is an if and only if statement. If these two vectors are orthogonal, right, then this angle is 90 degrees. Because that's the definition of what orthogonal is. So if this angle is 90 degrees, then these two vectors are orthogonal, right? So since this equation has to hold, regardless of what the angle is between these two vectors, provided that those vectors are non-zero, meaning that they have some length, either, you know, I mean, length is always positive. So as long as they have some length, this left-hand side of this equation will reduce to zero. So this is in the case where, and a little shorthand, if and only if U is orthogonal to V. And this is kind of a geometry symbol, which means at right angles. But I think we understand what that means in this context. So if they're orthogonal, this is sort of the mathematical notation of this. If two angles are orthogonal, then this ratio equals zero, right? Now, since neither U nor V are the zero vector, these are positive numbers of some kind. And so this equation reduces down to U dot V equals zero. So here's the test. If you want to see if two vectors are orthogonal, you simply compute their dot product, which is relatively easy if these vectors are in component form. And if that angle equal, if that dot product is equal to 0, then these things are at right angles. Now, if they're not, then there's some extra techniques you can do in linear algebra to subtract out the part that is not at a right angle. And so you can artificially create orthogonal coordinate systems. So this is sort of the big picture of why this matters. And it's certainly not illustrated in the textbook. However, we can use this test so that if the dot product is 0, these two angles are orthogonal. If the dot product is not equal to 0, then these two angles are not, or sorry, if the dot product is not 0, then these two angles are not orthogonal. And that's really what comes up in the textbook, is that question of, are these two vectors orthogonal? So let's just check real quick. Here's an example of one that we could use. So is U orthogonal to V? That's kind of the shorthand for this. And let's say U equal to 3, 4, and V equal to -2, 1. Now, let's just draw these real quickly just to see if it's, I mean, it might be that it's not even possible, but let's just see what these look like. So we've got U is a vector that's pointing into quadrant 1. It's got an x of 3, y of 4, so it's up there somewhere, right? And then V has an x component of -2, but a y component of 1. So it's kind of this little short thing here. Now, it's possible that these are orthogonal, but this is really the test. So if we run this test, let's see. So if we take the dot product, we multiply the two components together. So we have U dot V equals what? -2 times, well, I did it backwards, but that's okay. So -2 times 3, and then plus 1 times 4. And notice that this equals -2. So it doesn't equal 0, which tells you that these two vectors are not orthogonal. So U, and there's a way to write this with like a slash, which is kind of weird when I've got a thick marker like this. But another way to say it is, they are not orthogonal. But notice that this kind of gives us a setup to figure out what could be an orthogonal vector, right? So if you wanted to, for example, if you wanted to find an orthogonal vector, and this is maybe a little bit of an expansion of where we're going. So, and this sometimes does come up when you have a vector in a preferred plane. You might say, okay, well, can you construct a vector orthogonal to V, or let's make it W, so we've got some different one, where W is equal to -2, 4. Well, it's pretty easy to do this because all we'd have to do is we say, okay, well, how about I just pick a coordinate and say, all right, well, how about the orthogonal, let's just suppose is 1, and then we just have to figure out what this x value is, maybe call it y, because it is the y component. So we could write an equation to be able to do this. You'd say, okay, well, so if it's orthogonal, then W dot W orthogonal equals 0. But we know that the dot product is equal to the product of these components. So that's -2 plus 4 times y, right? And now we just solve this. So we could have, we could solve this equation for y pretty quickly. We'd get that 4y is equal to 2, so y equal to 1/2. And if we put this y back up in here, you now have an orthogonal vector. It's not the only one, because there's a choice of whether we have a positive or negative number here. If we'd have chosen -1, we would have ended up with y equal to -1/2, which is actually sort of the mirror image of those two vectors. So, but pretty quickly, like I said, and if you wanted to take something that was a little bit bigger than this, so you don't have fractions, it turns out that if a vector, if W is perpendicular to the vector U, then A times W is orthogonal to B times U for all A and B not equal to 0. So it doesn't matter if you multiply them by a scalar, you end up with the same result, which is kind of a long-winded way of saying that, yeah, I could write this perpendicular as 1, 1/2, or I could just double it and say it's equal to 2, 1. And I think you can verify pretty quickly that 2, 1 is also orthogonal to this vector. So anyways, that the next step, and this is something I certainly don't want to go into, the next step that you would do in trying to create a sort of an arbitrary coordinate system is you start by normalizing these vectors, which means that you divide them by some quantity to give them a magnitude of 1. So then you're creating sort of artificial unit vectors. And then once you have artificial unit vectors that are all orthogonal to each other, you can now operate in some new space that maybe is not aligned with the normal XYZ coordinate system, but has all of the same benefits of it. So anyways, this has been a little expository in its concept of orthogonality. I don't want to bury you too much in details, but there are a couple problems in the homework that I usually assign that are just check to see if they're orthogonal, which is a pretty easy step, which is a pretty easy process. You take the dot product and you ask yourself, is it 0 or is it not 0? If it's 0, the two vectors are orthogonal. If it's not 0, then they're not. All right, this has been it. This is the last segment for chapter 7, specifically sections 7.4 and 7.5. If you guys are interested, I have included also an expository on spherical trigonometry, which is something that is certainly not in the book, certainly not required of the course, but something that I really enjoy doing. So I will see you all around. Good luck.